theory. So we're going to take the electromagnetic spectrum and the information we've learned about the electrons and the orbitals and take it a step farther. So in 1923, Louis de Broglie proposed the particle wave duality of matter. Now, this was a huge step, duality of matter, because when you look at it, moving particles then have a wave nature, and they use the term matter waves. So when you look at this, the equation is the wavelength is equal to Planck's constant divided by the mass and the velocity. So what that truly means is that your wavelength is associated with your mass and your velocity. Now, if you think about it, the greater the mass, the smaller the wavelength. So with certain things that are really large, they're too large, and the wavelengths are so small that with the equipment we have today, they really can't be measured. But they can exist. Now, what do we know that has a very, very small mass? Electrons. So we have the dual nature of electrons. And so what we find is electrons are going to behave as standing waves. And because they are standing waves, the energy is moving along the wave nature, okay? And the energy is traveling along a non-moving wave, not the particle. So the point being is if you look at particles, that's down here. If you've got a whole bunch of particles, let's think of BBs that you're shooting through, then when you move them through the slit, you're only going to have two areas where they're going to impact because they come straight through the slit because they're particles. Waves, on the other hand, are going to constructively and destructively interfere, and so you're going to get a light and dark pattern. So when you run electrons through slits, they don't behave like particles, they actually behave like waves. So that brings us to the first of the principles, which is the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle states that it is impossible to determine the position and the momentum of an electron simultaneously. What's that mean? So the example I use is a photograph. Let's pick a city. We could pick downtown Macon because it stays open pretty late, assume non-COVID. If you're able to be a drone and you're perched over a busy intersection and you take a picture, then you can know where the cars are in the intersection, but you have no earthly idea how fast they're going or what direction they're going. Let's assume that you eliminated all the brake lights. So you can take a snapshot. You know where they are. You don't know which direction they're moving or how fast they're going. So we know where they're at. Now let's hang over the same intersection, and now let's take a time-lapse photo. So what you see is the cars moving through the intersection. You can see where they're going. If you take the time interval and the distance traveled, you can get a speed or rate of movement. You can get a directionality because of where they start and where they end. But you don't have a clue where they are at any instant because the speed you're calculating is an average. How do you know that they weren't slamming on brakes, slamming on the gas, slamming on brakes, slamming on gas? You won't see that in a time-lapse photo. So you can either know how fast they're going and which direction they're moving, or you can know their position at any given time. But you cannot know both. So we cannot know the position and the momentum at the same time. So that brings us to, do you remember several slides ago when we said that we don't talk about an electron as knowing where it's at. We talk about the probability of finding an electron. Well, if you take a baseball, think baseball, and you throw the ball, you can follow the ball where it goes. That's what's called a classical trajectory. The problem with then being an electron, it has a particle and a wave nature. So as it moves, remember a wave, think of a flashlight, will spread out. Particles have one place. So if you notice that it's actually darker in this little area where I just put the line, but there's a probability above and below that. So we call this a probability distribution. So an electron, instead of saying it's right here, spot A, same spot pretty much, you're talking about a probability of where you're going to find that electron. So when we talk about electrons, we talk about the probability of finding one, not it's right there. Closer look at this measurement in the uncertainty principle, you can look at that. That brings us to Erwin Schrödinger, who did a mathematical solution. It is called a wave function, and it has the symbol psi, and it combines the wave and particle nature of the electron. In a hydrogen atom, because remember we set this up for hydrogens. Okay? And if you have the psi prime, that's the energy of the electron. So, if we take this mathematical operation, now, you need heavy calculus, advanced calculus to do this. So your take-home message is that you need to know that Schrödinger's equation is very important because it combines mathematically the wave and the particle nature of the electron. So here's the thing. It was a very important equation, but the problem with it is what do you do with it? Well, Max Born interpreted. So he came along and he took Schrödinger's equation and said, wait a minute. And again, this thing is called the wave function. And he said, let's square it. If we square it, we get what's called the probability density, which is the probability over the unit volume. And so this square gives you the probability of finding an electron in a particularly small volume of space. So Schrödinger's equation combines the particle and the wave nature of the electron. However, there's not a whole lot you can do with it until Max Born comes along and he says, wait a minute, if we square this thing, then that gives us a probability density so we know approximately where the electron is located. But again, we can't say it's there. We have a probability of finding it there. So that brings us to some things we need to talk about with respect to the electrons. So when we talk about electrons, one of the things we're going to talk about is ground state. This is the lowest energy level for that electron. Now, electrons can be found a variety of places within an atom, assuming there are multiple electrons. Okay, so the ground state is the lowest energy. So the first energy level is n is equal to 1. So the ground state is this position right here, or this position right here, or this position right here. If it's in an excited state, then the electron has absorbed energy and move to a higher energy level. So we say it's excited. So for example, if this is the ground state of this electron, but we move it up to here, then we say that this electron is excited. If I could spell excited. Okay, so that's the excited state. Notice that it kind of matches, it does match color. Okay, ionized means that the electron is lost. That means the energy between the electron, the attraction between the electron and the nucleus is zero. So that's when we go to infinity. Okay, so it is going beyond the orbitals. It is lost to the electron. So when we start talking about electrons, if they're where they're supposed to be, lowest energy, where they're supposed to be, that's the ground state. You give them extra energy, they're going to move up. That's the excited state. Now, the excited state, they don't stay there. It's kind of like you climbing up on the top of a slide and sliding down. You're going to come down. And then if you go all the way past, you're ionized. Now, we're going to talk about the quantum numbers in this chapter, and then in the next chapter, we're actually going to apply them. So, hang with me and we will talk about it. Now, before we get to the quantum numbers, what are the quantum numbers? Well, the quantum numbers are the four numbers that will allow us to identify each and every electron in every atom. It's kind of like getting your mail. Your mail comes to your house. If you live in an apartment, you have 5 apartments, you're in apartment 4, it'll come through the same address, apartment 4. If you're living in the house with your parents and you're a junior and your father's a 1, and let's say let's make your father a 2 and you're a 3, and your grandfather lives with you now, so he's the 1. When the mail comes, you if you're John Doe, you look for John Doe 1, 2, or 3 to specify which John Doe you need. So the bottom line is when we talked about quantum numbers, they're just ways to identify each species. So the first thing we're going to do is define the terms, and then we're going to go through each one. The first orbital quantum number, and there are only 4 that we use, is the principal quantum number. It has the symbol N. Okay? It's going to describe the orbital energy level or its size, because the levels go out like layers of an onion. The angular momentum, the old terminology was the azimuthal quantum number, and since I took classes back in the dark ages, I will refer to this as azimuthal as angular. Angular momentum, it's really funny because it took me a minute to find this, but if you're talking about an angle, you refer to that in the old terminology of math as the azimuthal angle. And so azimuthal basically means angular. So same word, different thing. So this value has L. And to differentiate, I usually use the cursive L. And if the first one describes the energy level, the second one is going to describe the shape. The third energy level is going to give you the orientation of the orbital in space, because some orbitals only have one orientation and some have multiples. More about that as we look at them. So that levels that down. And then the last one is the spin quantum number, and it's going to describe the direction of the spin of an electron. Okay? And that's the one that's going to narrow it down the most, and we'll get to that in just a second. So we've defined all of them, so let's go back and explain each one in more detail. So the first one is the orbital of the orbital quantum numbers is the principal quantum number. That is the energy level, and that describes the orbital. So the first energy level is 1, 2. Now, you can't have anything below 1 because if you're below 1, you're in the nucleus. And when I do this, I have a periodic table handy. So as I describe things, I'm going to reference the periodic table. So if we're looking at it for the periodic table, N equals 1 is the row with hydrogen and helium in it. So it's row 1. 2, it would be row 2. So that's going to go from lithium to neon. And row 3 would be sodium through argon. Row 4 is where we will first start to kick in the transition metals. So we'll have potassium, calcium, scandium, all the way through to krypton. Now remember, I'm getting these from your periodic table. So as I'm doing this, I'm literally I'm writing with one hand and holding the periodic table with the other. If you do this with the periodic table, then you will always hold on to how it works easier, and you don't really have to memorize anything. And I'm all for not memorizing stuff. Okay? So, the next quantum number is the angular momentum quantum number. Okay? And it is L. So, what L is remember we said that N started at 1 and went up. Didn't start at 0. Well, L starts at 0 and it goes up to N minus 1. So if N is equal to 3, L can be equal to 0, 1, or 2. And what is L? L is the shape. So if L has the value of 0, it's an s orbital. If it's 1, it's a p orbital. 2, it's a d orbital. 3, it's an f orbital. Now, we really don't have g's and h's, but we can propose them. That would be L equals to 4 and L equals to 5. So if n equals to 1, there's only one option. It's the s orbital. So if you look back at the periodic table, remember this is hydrogen and helium. So there's only one option. For row 2, you'll have 2 that are in the s orbital. That's lithium and beryllium. Whereas the 1 is the p orbital. And you're going to discover in just a second there are 3 p orbitals. So that would be aluminum through, no, skipped a row, sorry. Well, it would be on the second row, but that would be boron through neon. So for the third energy level, the 0 would be sodium and magnesium. The 1 is going to be the p orbital, and that will be the aluminum through the argon. And the 2 starts the d's. That's the scandium through the zinc. So the bottom line is as we go through our quantum numbers, we're identifying each electron as we go. So as we start adding them in, so for example, I'm looking at magnesium, which has an atomic number of 12. It has 12 electrons. That means we have to identify each and every one. Okay? So as we go through, let's take it to the third magnetic quantum number, and it is M sub L. It describes the orientation. It's the magnetic quantum number. It's the orientation in space. And so the value for that is negative 1 through plus 1 through 0. So if L is 0, M is 0. If L is 1, then M sub L is minus 1, 0, plus 1. If it's 2, we start at minus 2, 1, 0, 1, 2, 3. Okay. And remember, this is the S, these are the, whoops, no it's not. I'm just, stop that. Okay. This is the P, this is the D's, and these are the F's. Okay. So now, there are 2 electrons because of the spin. We'll get to that one in just a minute. So 2 electrons per orbital. So that means there are 2 here. In the P, I have 3 times 2. That means I have 6 electrons. So if you'll look at the grouping, The 2 electron group is the group 1 and group 2. The 6 member group is that chunk of boron through neon. So on your periodic table, it looks like this. So this will be the S, this will be the P, and I have a slide of this later. This will be the D's. So if you'll notice, we have 5 of these orbitals times 2 electrons, so we have a total of 10 electrons. So if you count across from scandium to zinc, guess what? You're going to count 10. And then this one has 7 orbitals times 2, so there are 14 electrons, and that gets us to the lanthanide and the actinides. More about that in just a minute. So what we're doing is relating the quantum numbers to each other. So then that brings us back to the orientations in space. So this is an s orbital. And you can think of it as S standing for sphere. Doesn't work for anything else, but it does work for S's. So basically, it's like a ball. So if you were to take a bouncy ball and cut it in half, then what you would see is you would see a really thin membrane where you had a set area where you have, the vol vinyl, whatever you want to call it. Okay, that is the orbit. That is the probability of finding an electron. So in 3D, it's a sphere. If we cut it in half, then it looks funny. So what we look at is from the distance from the nucleus. So here's your nucleus. You get an area where you have high probability and then it's low probability. So you go out and then it's like, oh, what? There's an electron. We're not. Okay? So that's an s orbital. And that brings us to one of the properties of waves that you have to understand, because we're about to look at it, is if you take and pluck a string here, it is like it will set up a energy level. It'll go back and forth like a guitar like a guitar string, and you'll get a particular sound. Well, in this case, you'll get a wavelength associated. Now, as it crosses back over the fundamental center line, then it has no energy. Okay? So this is a node. Now, a node is a zero probability of finding an electron. So when you look at orbitals, anytime it crosses the plane, then that will be a node. So when we start, there's no node in this first one, but as it crosses it again, rolls back and forth, you have a node. It does it again, you have 2 nodes. So when we look at electrons, we have to look at these areas. Now, that brings us real quickly to Schrodinger's cat. And this is, okay, if you've read my door. Oh, wait, you haven't been here. Okay, on my door is a kind of a joke that is just the famous Schrodinger cat joke. Well, it's not a joke. It's a thought experiment. And what Schrodinger said is if you take a cat, and there were no cats killed in this thought experiment, okay? You take a cat and you put it in a box, and the box can be perfectly isolated. In the box is a radioactive substance that, if it decays, will break a vial of poison and kill the cat. So the question is the cat dead or is it alive? Well, the box is perfectly isolated, which means you can't hear the cat, you can't see the cat, no cheating. So the only way to find out if the cat is dead or alive is to open the box. Well, once you open the box, you force the isotope to either decay or to not decay. It's got to go one way or another, and basically you force the decision. So as long as you don't open the box, the cat is both alive and it's dead because the sample decayed and it didn't decay. So the problem is the cat is both dead and it's alive. Well, how can that be? Because we want to live in a black and white world. The cat's dead or the cat's alive. But in the case of quantum mechanics, with the wave and particle nature of the electron, you can't know both simultaneously. Remember, we can't know the position and the momentum simultaneously. We have to pick one or the other. So what happens is when we run an experiment, we predispose the electrons to act as either a particle or a wave. They can't act as both simultaneously. So the cat is both dead and alive. So what this means is that when we start talking about electrons, and we're talking about probabilities, then for s orbitals, they're like layers of an onion. You put one over the other. So here's the first shell, here's the second shell, here's the third shell. In between each shell, so if you were to cut this across, it's kind of like nesting dolls. You would see them together. There's your nucleus in the center. So this area here, and this area here, and this area here will all be nodes. So you don't have a node within the orbital, but you have nodes in between the orbital. Now, it may be a little easier to see on this one, and this is in the closer look, and they're cross-sectioning it. And so basically, here are your orbitals. There's one, there's the other one, there's the third. So in between each orbital is a node. So that would be a node area, and that would be a node area. Okay, so you look at them. And again, this uses your probability functions. We can't say, oh, look, the electron's there. This website, www.orbitals.com, it still has some good orbitals, but it's also split out, shall we say. Years ago when I first used this, it just did orbitals. And they kind of got into probability theory, and guess what happens when you get into probability theory? Gambling. Okay, because you start probability of getting this card or that card or whatever. So be careful if you go to this site. There are lots of other ones. You can just search orbital diagrams. But I like this one because it had a cutaway of the orbitals. Now, that's the s orbital. This is the p orbital, and with the s orbital, it's a sphere. So with the p, we represent it as a dumbbell. Okay, so basically, if you look at it, it's a line. So it's just a line. Well, you're probably sitting in some room. Find a corner of the room. And if you look at the corner of the room and you look at the number of lines that come together, you can have one that comes in the x direction, the y direction, and then the z direction. So if they go straight through, there's your intersection. So what we see is that we have basically the p orbital is linear shape, so we have three orientations in space. So remember, for a p orbital, L is equal to 1. M sub L, remember, was minus 1, 0, and 1. So look at that. So we have PZ, PX, and BY. That means they're in different orientations with respect to the z-axis, the y-axis, and the x-axis. So with the p orbital, we have three different possibilities of orientation. So we have three p orbitals. With the sphere, we had no possibilities. It was a sphere around the three-dimensional center. But with p's, they're lines. Okay? So for the d's, we say that the d is a double dumbbell. Okay, wait, let's go back because I forgot to point something out. Notice that if I draw it here, we have a node. Okay, there's a node in between those two lobes. So the electron goes from one lobe to the other lobe. Wait, how did it do that? Because the nucleus is in the middle. So one of the things that nobody really understands is how the electron gets from one side to the other side without going through the nucleus, because it's a solid going through a solid, or is it a wave going through a solid? So bottom line is there's a node right there. in between the two lobes. So if we have a d orbital, and I guess I could draw this a little bit better. Okay, we have two planes. So we have basically two nodes. So we have nodes, and again, that operates around the center point. Now, if we have the double dumbbell, it's kind of like a flat plane. So we have one in the ZY, one in the XZ, and one in the XY. Those are your flat planes, and then of course we have one here. Just go with it. You're just responsible for the basic shape. So a P is a dumbbell, an S is a sphere, a D is a double dumbbell. And then this is what I like to call the Jetsons view. Here are the Jetsons. It looks like the Jetson thing. So you have the lobe and you have the inner tube around. So that's the wild one. So remember, for D's, L is equal to 2. So M sub L is equal to -2, -1, 0, 1, and 2. So that's how we get the 5. Now, if we move up to the F's, the most common is the octuple, which is the 8 dumbbell. And no, okay, I'm really bad at drawing that. So this is a quadruple dumbbell or an 8 lobe. And so you have 4 of them here, because for this one, L is equal to 3, so M sub L is equal to -3, -2, -1, 0, 1, 2, and 3. So here we have 7 options. Most of them are like this. Here you have the funky Jetson. It's linear and it goes in different orientations. You're not responsible for the top ones. You're just responsible for the idea that it's a double dumbbell. Put them all together at this www.orbitals. There's a node here, there's a node here, node in between those two, and in the P, the D, the F orbitals, we have a lot more nodes. Okay, so we have taken care of the energy, the shape. The orientation allowed us to split out the shape. And now we need to do the last one, which is the spin quantum number. Now, spin quantum number is kind of the easiest, because your options are plus or minus 1/2. So you can either have plus 1/2 or minus 1/2. And it doesn't matter which way you go with them. Okay? And the reason why it works this way is that, remember way back at the beginning of the chapter we talked about the electromagnetic spectrum, and if we had an electric field, then we automatically generated a magnetic field. Well, guess what? Well, it's an electron. It's a negative charge moving, so it generates an electron field, which means if you put it in a magnetic field, it's going to make it flip or pop around. Now, this is actually useful because magnetic resonance imaging. Magnetic resonance imaging is actually nuclear magnetic resonance imaging, but they took the nuclear off because it was freaking people out. But basically, what you do is you get in the really, really strong magnet, and if you've never had one of these done, if you're claustrophobic, you're going to have a problem. If you're not, you may get that way. Shut your eyes. That helps. Trust me, I've had way too many of these suckers lately. But what happens is when you put it in the magnetic field, you make all of the atoms align a certain way based upon their spin. And these things are loud because what you're going to do is you're going to pop all of these spinning protons with a radio frequency current. And what that does is it's the equivalent of taking a spinning top and smacking the top of it. It makes it flip. And so then, as it slowly decays back to its original position, they can measure how much and how long, etc. And what that allows them to do is look at different structures in your body, not bone, based upon the hydrogen content. Well, hydrogen is in water, so basically the more water, the better for this. So that's MRI, and that's why it's really loud, and you can't have any metal. So, how do we put all these things together? So again, we're going to consider the quantum numbers and we're going to relate them. So remember, we're going to start with a principal quantum number. So the shells are the number of the energy levels. So remember, if it's n equals 5, if you're looking at your periodic table, you go down 5 rows. 1, 2, 3, 4, 5. So that would be the rubidium row going across. So what you're going to do is your shells are based upon your n. So you'll have n equals 1, n equals 2, n equals 3. And let me actually write this a different way so that I can take it down. So we're going to have n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. So how many shells are we going to have in this lever? 1, 2, 3, 4, 5. 5. There will be 5 shells. Now predict the number of subshells. Well, the number of subshells is, a subshell is the L value. So the energy level, the shell is the N value. So that means if N is equal to 1, remember L can be up 0 up to N minus 1. So for 1, L is equal to 0. For 2, L is equal to 1, 0, and 1. For 3, it's 0, 1, and 2, 0, 1, 2, 3, and 0, 1, 2, 3, 4. So when we look at it, we're now up to the subshells. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15. So we actually have 15 subshells. Okay? So then it says to identify each of the subshells by its number and letter designation. Well, this actually isn't hard. The number is the N value. That's the principal quantum number value. And the letter designation, remember, is L is equal to 0 means it's S, etc. So what this one would be is this value would be the first energy level. It's 0, so that's a 1s. Okay, this is the s orbital in the second energy level, so that'd be the 2s. P, if L is equal to 1, that's a P. So over here, whoops, we're actually moved to the third energy level, so we're a 3s, 3p, 3d. Here it's 4s, 4p, 4d, 4f. 5s, 5p, 5d, 5f, and if we had them, it'd be a 5g. Okay, so if you notice that it all streams down from N, L, and that's 1 up to, and this is 0 up to N minus 1, and then M sub L is equal to minus L up to 0 through to plus L. And then we would do M sub S, which doesn't play into here, other than we could say that each orbital has, each subshell, and this would be a shell. Your subshells are each group. Again, if you look across your row for the third energy level, that starts with sodium. So sodium and magnesium would be the S's, then aluminum through argon would be the P's. If you go down, then you add in the D's, and we'll get to that as we go. So that brings us to the definitions, and we've already actually kind of talked about them. So the orbital are the regions in space where electrons are likely to be found. So that means they have a high probability. And, well, that's an orbital. These are regions in space. Now, an orbital is defined as 2 electrons. We'll get to that in just a minute. but there are only 2 electrons per orbital. Okay, a shell is ones where they orbitals that have the same value of principal quantum number. A principal quantum number. That means n. They have the same value of n. They're all in the same shell if they have n. So if 1s would be in a shell by itself. But let's go to 3. So 3s, 3p, 3d, those would all be in the same shell. A subshell is orbitals that have the same value of angular quantum number. Okay, remember that's L. So if they have the same angular quantum number, so they're all zeros or they're all ones or they're all twos, they're in a subshell. Okay, and the total number of orbitals in a subshell are 2L plus 1. I don't rarely use that. So in a node, remember, is a region where there is 0 or no chance of finding an electron. I refer to it as a no-fly zone, but that wasn't. Okay, so we know now how to define an orbital, a shell, a subshell, and a node. So that brings us to the next list. Degenerate orbitals have the same N and L value, but differ in the M sub L. Because what these all have is they're in the same energy level. The only reason they differ is they have differing orientations. So the ones that can have different orientations in space are P's, D's, and F's. S's are not degenerate. Degenerate means they have the exact same energy, they just differ in orientations. Isoelectronic species are species that have the same electronic configuration for different species, and we'll go through a variety of these. And they're not going to be electron or atoms. You're not going to have 2 elements that have the same electronic species. You're going to involve ions, etc. Okay, the electron configuration is going to describe the electron distribution in an atom. So basically what we're using is these 4 quantum numbers to allow us to differentiate all the electrons in an atom from each other. So the question is how do we do this? Well, the first thing we've got to remember is that we're operating off of the Bohr model, which was based strictly on hydrogen. But these are going to differ from hydrogen because they all have more than 1 electron. Is all subshells of a principal shell do not have the same energy. And we'll look at this when we start to fill. And the reason why is because they're going to interact with each other and they're waves. And if you want, it might be easier to think of magnets. If you set different strength magnets next to each other, they interact and they affect how they connect to each other. So the same thing is going on in it, but it's waves. And it's the energy associated. Now, orbital energies are lower in general if you have multiple electrons because they start to level out and stabilize. All orbitals within a subshell are at the same energy level. Now, we say level because they're not all exact energy, but they're incomparable. Higher principal shells, some subshells with different, oh boy, that's spelled wrong, different principal numbers have similar energies. Okay, so some subshells with differing principal numbers will have similar energies as they go through. So let's look at a periodic table when we do this. So what happens is the 1s energy is fine. That's first energy level. Then here's your second energy level. And here's where it starts to get weird, is at the third energy level. Because if you look at the third energy level, you have sodium and you have magnesium. And then you move over to aluminum through argon. Then you move to the 4s, and then you move to the 3D. So technically these should all be in the same row. The problem is because of the multi-electrons, the 4s is at a slightly lower energy than the 3D, so the s's fill before the d's. There's a practical effect to that, and I'll show you that in a figure. But the other effect of this setup is that you have a maximum capacity of electrons in each subshell. So if you look at row 1, that's hydrogen and helium. It maxes out at 2. Lithium through neon has 8 electrons. You're like, wait, but neon has 10. Yeah, because it has hydrogen and helium, those two, and then it's 8. And then the next group is 18, and then it's 32, etc. So how do we describe how these fill, or where the electrons actually are? Well, we use what's called the, this is a high tech, the SPDF notation. It's going to designate the principal shell, the orbital subshell, and the number of electrons. Okay, so it's going to tell us the principal energy level. So these numbers out front tell us N. That's the principal energy level. The S's and the P's will tell us the subshell. That is the azimuthal quantum number. So this is L equals to 0 and this is L equals to 1. So we know what our principal is, what our azimuthal, and then this exponent here shows us the number of electrons. So the proper format is those are superscripts. And if you add all the exponents together in an electron configuration, that will tell you how many electrons you have in the structure. So then the question becomes, okay, how do we fill this? How do we know where those little discrepancies are to add in? Well, the easiest thing is to set it up. First row, we only have S's, then it's S's and P's, S's, P's, and D's, etc. So if we start in the upper right-hand corner and go down, we're going to fill the 1S first, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, and on down the row. So if you look at the filling order, it's 1S, 2S, 2P, 3S, 3P, 4S, then 3D, 4P, 5S, 4D, 5P, 6S, then 4D, F, and then on down the row. So before we can actually do more, we have to talk about two other rules. The Pauli exclusion principle states that no more than 2 electrons can occupy an orbital, and if there are 2 electrons in an orbital, the spins of the electrons must be paired. Huh? The practical effect is that there are no two electrons in the same atom can have all four quantum numbers the same. Now, we say that the electrons must be paired. What's that mean? Well, remember they can be plus 1/2 or minus 1/2. And we often talk about those as spins. Now, it doesn't matter which one's up and which one's down. But think about boots, putting them back in a box. Now, boots don't tend to stand up. You have to put heel to toe in and heel to toe to heel. You can't put both feet side into the box at the same time. They have to pair. And so that is the same true with electrons. So that when they go into an atom, you cannot have all four quantum numbers identical. Now, the last rule is Hund's rule, and I tend to call that the bus rule. But what it says that electrons enter each orbital in a subshell singly, that's actually a word, before double filling. And electrons add to each orbital in a subshell with the same spin until each subshell has at least one electron. So what that means is if we talk about electrons having spin, there's up spin and there's down spin. Now I call it the bus rule because if you go get on the bus and you have to sit in the seat and you don't know anybody on the bus, you're going to sit in an individual seat by yourself. Think of two-man seats on buses. You're going to sit in a seat by yourself until there is no other empty seat left, and then you will start to double fill. Now, the only thing you don't do is stand on your head, because what they're saying is the first electron goes in, the second electron goes into the second orbital, but it has to have the same spin. And so I'm designating one spin as the up spin. So the third one will go in. Now, when the fourth one goes in, it has nowhere to go except to double fill. So you're going to pair your spin. You could have started with the down spin, and you can do 2 arrows or whatever, and then it's going in. And so this one's going in this way, and whoops, can't do that. This one's going in this way. You cannot have two with the spin the same. That's a no. They have to be paired. So if you start up, you go down on the other side. If you start down, you go up. Does it matter which one you do? No. But you can go up or down. And so that's Hund's rule. And what Hund's rule makes sure of is that you have no more than 2 electrons in each. Actually, that's not true. Pauli exclusion principle makes sure you only have 2 electrons in each orbital. Hund's rule makes sure that you pair spins as you go through it. Now, we have talked about the quantum numbers. What we're going to do in the next chapter and the next section is to actually walk through and look at each element and do the quantum numbers associated there. So this is one of those cases where the first chapter actually is going to spill into the second chapter. Normally this is kind of together in the same chapter, but this text split it apart. So we're moving from one chapter into the next chapter. And once we do the electron configurations, we strictly do trends. And I'm going to warn you right now, before you start the next section, you need to go ahead and have a periodic table in front of you. You might want to be able to have one that you can write on, to have a clean one and one that you can write all over so that you can do different things on different ones.